Hello everybody. In today's class we shall discuss unweighted code. So, we have seen binary coded number, and we have seen that the weights associated with binary code is 1, 2, 4, 8, 16, so on and so forth before the binary point, and half, 1 upon 4, 1 upon 8, etc. after the binary point. So, we shall look into what is the need of having unweighted code. Then we shall discuss two important such codes, Gray code and XS3 code, and also we shall discuss ASCII code. So, if we remember a quick revisit of the binary code. So, 4 digit numbers B3, B2, B1 and B0. Okay. So, with that with the binary code, this formula you remember the corresponding values. So, for any number with base or radix r, so this is the digits and this is the corresponding value. So, if we consider this number 1010, and if it is 8421 code normal 2 to the power 0 etc., this way the standard way of associating weight, then the value will be for this one 8 will come, and for this one 2 will come. Okay. So, 8 plus 2 10 will be there. So, there can be other kind of weighted code where this is not exactly like this r to the power n, r to the power 1, in the way it is increasing the the integer power is increasing based on the position. Okay. So, there can be other way of putting weights. For example, if it is a 2421 code, so the first position associated with the digit will be having a code weight of 1, second position 2, third position 4, and the fourth position is having a weight of 2. So, that is called 2421 code. So, that is also a weighted code, because weight associated is 2. It is not 2 to the power 3 8 that we see for 8421 code. Okay. And 1010, if we are using 2421 code, what will be the value? So, the 1 in the this place B3 place will be having value 2, and then there is a 0, then there is a 2 for this particular one, and then there is a 0. So, 2 plus 2, the value will be corresponding decimal equivalent will be that of 4 for this 2421 code in 1010 representation. Okay. This part we understand regarding weighted code. Now, what could be the issue with weighted code for which we might need to look into different form of unweighted code. Okay. So, one of the issue that you can see in this particular case, so when we are changing the number from 0 to 1 to 2, so this is your 1, this is your 2, then 3, 4, so on and so forth, this decimal equivalent, the consecutive increase in the number. So, from 1 to 2, you can see that 2 digits are changing, 0 1 is becoming 1 0. Okay. So, from 3 to 4, you can see 3 digits are changing, 1 1 is becoming 1 0 0. Okay. So, what could be issue with that? So, this is the way the weighted code 8421 code, the way you have seen it is is there. So, let us see one possible issue with such kind of coding. Consider there is a conveyor belt, the one that you see here, okay, over which some material is there, and the conveyor belt is moving in this direction, right direction, as has been shown with the arrow. Okay. So, it is moving from zone 1 to zone 2, okay, for where some activities are taking place, and the conveyor is supposed to go in this direction, right. And if we are sending a binary code of the zone where the this particular material is lying at a given time to a control unit, okay, through a mode of digital transmission of data. So, from zone 1 0 0 1, it is going to 0 1 0. Okay, that is the way it will be kind of shown in that control room, right. Now, from 0 0 1 to 0 1 0, since these 2 digits are changing, if so happens because of various delay elements associated with the bit positions and the changing of the value, the coding of the value and its transmission, that this 1 is changing, okay, while this 0 has not yet changed. So, this 1 is changing faster than the 0 that is supposed to change to 1. They are not exactly changing in a same time, okay. And after that it is going to 0 1 0, of course, okay, after some delay. So, at some point of time the 0 0 1, okay, after that 0 0 0 will come, and that will make an interpretation that it has moved from zone 1 to zone 0, when it is supposed to go to from zone 1 to zone 2, isn't it? So, basically the conveyor belt is moving in the reverse direction. So, that might cause some alarm or emergency, some issues, okay, with this the particular thing. So, people would prefer in such a scenario for consecutive numbers that only one bit if it is possible to make change, okay. So, that gives rise to what we call gray code. So, in gray code, two consecutive numbers do differ by only one bit. So, the distance between two numbers in terms of bit position changing is only 1, okay. So, if we look at example of some gray code from the initial value, say 0 to 10, the way we had seen for binary code. So, these are the corresponding equivalent 0, 1, 2, 3, the consecutive number we already know 5, 6, 7, 8, 9 and this is 10, right. Now, corresponding gray code, if you see 0 is 0, right, there is no ambiguity about that. 1 is 0 0 0 1, absolutely no issue, because only one bit is changing, right. Now, here when it comes to, it is 1 0, 2 bits are changing, here it is 1 1, okay. From 2 to 3, this is 1 0, this is 1 1, from this 1 1, now only one bit can change. So, this 1 1 is now 1 0, right. So, is there any rule by which we can get this number from binary to gray, or some sort of way the number can be generated, okay, not heuristically. So, one such method is through reflection. So, how is it that let us see. So, first 0 and 1 we have no issue, two numbers 0 and 1 is getting represented in binary as well as gray. So, this 0 1 you reflect, okay, like this is a mirror. So, this is 1, this 1 is getting reflected here and this is a 0. Now, some additional bits are required because the number the count we are trying to increase. So, you put 0 0 0 in the first two and 1 in the second. So, 0 0 0 1 1 1 and 1 0. So, that gives you 0 1 2 3. You can see over here the first thing. So, first 4 number is obtained. Now, to get next 4 numbers, what shall we do? Again we will do the reflection. Now, we shall take these 2 digits together. So, 0 0 0 1 1 1 and 1 0. So, if we reflect, so 1 0 is reflected here, 1 1 is reflected here, 0 1 is reflected here and 0 0 is reflected there, okay. So, again we shall put zeros here and 1s here. So, by which the third digit comes into play. So, that will give us 8 such consecutive numbers. And similarly, we can go for this 8 will be represented here. So, that gets reflected like 1 0 0 is reflected here, 1 0 1 is reflected here, and then we place the fourth digit here, first block 0 and second block 1, we shall get the consecutive numbers. So, that is the way we can get it, and we can see that the gray code is formed, okay. So, the to generalize, by reflecting n minus 1 bit gray code, we can get n bit gray code, okay. So, this is one way of getting the gray code, right. So, gray code in 10 is 1 0 1 0, this is 1 1 1 1. Of course, you can understand that this is not a weighted code, okay. So, if you try to associate some way like 8421, 2421, any other way, you will see that it is not working, okay. But good thing about it is that the consecutive numbers are only increasing by one bit. So, there is no ambiguity of one of the bit is changing slower than the other, resulting in some interpretation of a different number coming in between, right. So, if we have a situation where the input is binary digit and the output is gray code, I mean that is what is required, and then how we go about it, okay, how we can get the codes converted, and also vice versa. I mean, like we have gray code, we want a binary code, right, for some reason, for some application. So, to do that, if we look at the the mapping, we can come up with a very simple relationship where the nth bit, the most significant bit, right, if it is a n digit conversion that we are looking at, that will the gray code of that and the Bn will be exactly the same. Okay. So, here if we take this 4-bit example, so B3 and G3, so G3 will be same as B3, right. And for other values, okay, Gi is Bi plus 1 XORed with Bi. Okay. So, what does it mean? So, B3 straight away goes as G3. So, G2, okay. So, the next gray code is Bi plus 1, this is 2. So, B3 XORed with B2. Okay. Then we shall get this one. B1 is B2 XORed with B1. I mean, same way B1 and G1 will get B2 XORed with B1, G0 will get B1 XORed with B0. So, if we just put it into the form of a bank of XOR gate, you can get it in this manner, and we can see that this is working. For example, if you say first case, so all 0, right. So, 0 comes over here, right. So, the 0 0 0 0, you can say this is 0, 0 0 XORed is 0, 0 0 XORed is 0, 0 0 XORed is 0. So, no issue, right. So, next one is 0 0 0 1, we can see 0 0 is 0, I mean 0 comes here is 0, 0, next one is 0 0 XORed 0, next one is also 0, and 0 1 XORed is 1. Okay. Now comes when there is a difference. So, binary code is 0 0 1 0, right. What is happening now? Shall we get 0 0 1 1? Let us see. So, 0 comes over as 0 directly, 0 0 XORed is 0. Now, 0 1 XORed is 1 and 1 0 XORed is 1. Okay, that way you can verify rest of the numbers, and you will see that such a simple circuit will work, okay, as a code converter. Now, for gray code to binary code conversion, so if you look at the reverse way the mapping is done, we can see that G3 can directly go as B3, and second bit like B2 can be generated by XORing G3 and G2, and B1 can be obtained by XORing B2, the output that has been generated, okay, using with G1, right, and B1 XORed with G0, we can get B0. Okay. So, you can again put those values and can see that this is the way simply we can get the binary code generated from the gray code. Okay. Now, we come to another kind of code which is called ASCII code. So, here we are trying to represent BCD numbers, binary coded decimal. So, 0 to 9, these are the 10 numbers. So, in binary coded decimal we have 0 0 0 0 to 1 0 0 1. Okay. So, in ASCII code what we are doing, this 0 to 9 is represented by 0 0 1 1 to 1 1 0 0. That means, whatever is the binary code, add to that 0 0 1 1, we get ASCII code. Why? Why are you doing this? I mean, what is the benefit out of it? It will be clear very soon. Okay, we shall discuss that part. So, first we see that how it is represented. So, this is the way it is represented. So, if we are representing a number 5 3 in BCD code, it will be 0 1 0 1 for 5 and 3 0011, isn't it? But in access3 code, this will be add 3 0011. So, this is 1000 and this is 0110. Okay. So, you can see that 5 is 1000 and 3 is 0110, right, 5 and 3. Okay. So, similarly 6.9, if you want to represent, again 6 is here, you can see 1001, right, and 9 here is 1100. Okay. So, this is the way, I mean the representation is there, and this is for many other cases. We can see, for example, if you want to represent 487. So, 4 is 0111 in access3, 8 is 1011 and 7 is 1010. So, this is the way the number will be represented. Okay. So, this is coming in competition with BCD code, okay, and accordingly we shall see the benefit, okay, in subsequent slides. And regarding code conversion, so how to convert from one form to another. So, one approach could be the case where each of these access3 code. So, if I represent them as x3, x2, x1 and x0, right, we can have a truth table where this is x3, what is the value of x3 for different representation of b3, b2, b1 and b0, right. And the numbers that are not there, like 10 to 15, right, 1010 at the input side to 1111. So, those are the don't care cases, okay, we do not care about what will be the value, right. So, with that we can have a minimization process, Karnaugh map, QM or Boolean algebra, by which we can get the value of x3, then we can get x2 and get x1 and x0 as a function of b3, b2, b1 and b0, and we can realize it. So, this is one way of getting it. The other one could be just having a 4-bit adder, right, a 4-bit adder by which you can add and get it. And the reverse process means from access3 to binary. So, we shall have b3, right, we shall see how it can be represented as a function of x3, x2, x1 and x0 for different values. Again we shall consider don't care and get the relationship and realized after minimization, or we shall have a subtractor by which we are subtracting 0011 from the access3 code, we shall get back the binary code. Okay. So, the benefit you will see over here. Okay. So, compared to BCD arithmetic, you will see that access3 arithmetic is simpler. Okay. So, let us see how the arithmetic is done. So, if we are looking at addition of say two numbers for which the no carry is produced, okay, no carry is produced, right, what is the implication of it? So, let us consider two numbers 5 and 2. So, corresponding representation is 5 is 1000 in access3 and 2 is 0101 in access3, okay, because 3 get added with normal the binary coding, right. So, if you add, so this is 1, this is 0, this is 1 and this is 1. So, no carry is produced here, of course, no carry is produced. So, we shall look at example where carry is produced. So, when no carry is produced, so this representation 1101, right, this is a valid access3 code, right, and this valid number, I mean valid number in the sense the number which does not produce any carry, right, but within it has two additional 3s that goes inside it, okay, one from here, another from here, compared to binary coding. So, basically what you get here is XS6, the binary coded number plus 0011 coming here, 0011 coming from here. So, if you want to get the XS3 version of the result, which is our intention, what we need to do? We need to subtract it, subtract 3 from it, right, because it is XS3. If we subtract 3, we will get XS3. So, the result will be, if you subtract from here, you get 1101 subtracted with by 3, we get 1010. Okay. So, this 1010 is the XS3 version of XS3 of the number 7 that we see as corresponding decimal equivalent. Is that clear? Right. So, when no carry is produced, the resulting number is a valid XS6 number. Okay. To get XS3, we have to subtract 3 from it, and that is how it is to work. Okay. And carry is not produced up to what? Up to 1111 when this result is there in XS6. So, that is your in binary, it is 1001. Okay. And that is your 9 in decimal, that is 1100 in XS3, right. Is it clear? And when it goes beyond 9, right, and this addition becomes more than 1111, so the carry gets produced. Okay. So, that is the in the binary coded decimal case is more than 9, basically we are getting the carry. Right. So, if you look at another example where carry is getting produced, so 5 and 7. So, this is 12. So, 5 is 1010 and 7 is 1010. We have already 1000 1010. So, if you add them up, we get 1 and 0010. Okay. So, how do we go about it? So, in this case, when carry is produced, so this is 0010, this is fine with normal kind of cases, right. But XS3 we have to add 3 with it, you have to add 3 with it. So, 0101 will be the case here, and for this one, if you are using this for another BCD addition, another XS3 addition, another such digit is there, so this will go as a carry. Otherwise, if it is the end of it, then we shall put it in the 4th bit, that means which is getting added with 3 basically. So, that is 1 and the 00 will come over here. Okay. That is the XS3 version, XS3 representation of 1. Okay. That is 0100, right. So, this is the way it will be represented. So, in what we see that in one case 1 is getting added, another 3 is getting added in this case, and 3 is getting subtracted over here. So, we just need to see whether the carry is present or not. Accordingly, the number 3, which remains constant, that will be either getting added or will get subtracted. So, that is going to help us in adder subtractor circuit for XS3 in comparison to BCD adder subtractor that we have developed before. Okay. So, if you are looking for addition of addition of numbers, decimal numbers with 2 digits. So, this is an example. So, 25 is added with 57. So, 25, 2 and 5 and 5 and 7, they are represented in XS3. So, this is the addition result. Okay. So, in that addition result here, carry 1 is generated. Okay. So, when carry 1 is generated, what we have to do for this particular XS3 digit, okay, of the decimal number, we have to add 3. So, that is what we will get 0101. So, 0101 is the decimal representation of 2. Okay. And when you add carry over here, by which what we see the number is 1110, and no carry is produced here, no carry is produced here. So, if no carry is produced, we shall follow this. So, 3 is to be subtracted. If you subtract 3 from it, we get 1011, and this 1011 is decimal equivalent of 8. So, the final result is 82. Okay. So, XS3 adder unit. So, XS3 adder unit, so the example that I just discussed is over here in the left hand side. So, what we do, this is the basic adder 7483, and then these are the 2 inputs, right. If carry is generated, what is happening? This is another adder, Okay. So, if carry is generated, we shall add this is coming as 0, this output will be 0. So, 1 1 is getting added, okay. 1 1 is getting added, and this is the carry which might go to the next stage, and if it is the end of it, then you see this is 0, this is, if carry is generated, this will be 1 and this is 0 and this is 0. If carry is not generated, this is 0, okay. And if no carry is generated, then what happens? So, this will be 0, so this will be 1, and this one is permanently connected, and then this is 0, right. So, 1 1 0 1. So, this is 1, this is 1 0 1. So, what is this? It is the 2's complement. 2's complement, this 1 1 0 1 is 2's complement of 0 0 1 1, okay. Remember that, right. So, 0 0 1 1 1's complement is 1 1 0 0 plus 1 is 2's complement, which is this. So, we do not need a carry in over here in the adder, because it is already there, okay, right. And then we do 2's complement addition and we get the subtraction done. So, this is the way we can get very simply the XS3 adder circuit made, compared to, if you remember, BCD addition, okay. Now, coming to XS3 subtractor, one good thing about XS3 number is that if you just invert the number, invert the bits, individual bits, then you get 9's complement, right. You do not need, for BCD subtractor, if you remember, we discussed 10's complement generator circuit, or if we had used 9's complement, arithmetic, we would have used 9's complement generator circuit. Here we do not need a elaborate or more complex this 9's complement or 10's complement generator circuit, because the inverting the bits, we can get the 9's complement of it, okay. So, 9's complement subtraction we have already discussed before in an earlier class. So, we have just show the implementation here. So, say 9's complement of 2, right. If we look at, so 0 1 0 1 is in XS3, right, 0 0 1 0 in binary, XS3 0 0 1 0 1. If you take 9's complement of this 2, it is 9 minus 2, which is 7, and 7, if you just look at it, it is 1, if you 1 0 1 0 in XS3, and you just invert the bit here, you get the 9's complement, isn't it? And what is the process? If we remember, for 9's complement based subtraction, add 9's complement of the subtrahend with the minuend. If carry result is positive, add carry. Also add 0 0 1 1 for XS3, because if we want XS3, we need to add this one. If no carry, result is negative, and we have to subtract 3 for XS3, and we invert the bits, we get the result, okay. So, this particular block by which this shows the logic circuit by which we can get it, right. So, this is showing when there is a subtraction. So, there is a inversion getting done, okay. And this circuit is familiar, the BCD the XS3 adder circuit, right. And here what you can see, if there is no carry, result is negative, right, and subtraction is done and inversion of the bits. So, inversion of the bits is happening to give you the final result. Is it okay? So, compare with other circuit, we do not need, as I said, 10's complement generator and other circuit. So, this is why XS3 is useful, and of course, it is an unweighted code. And finally, this is ASCII code, where whatever we are working in the computer, or the computer is talking to a printer and all. So, in that case, the control values, control codes, and alphanumeric codes, the printable characters, etc., these are all generating ASCII code for communication from one place to another. And ASCII code, the full form of it is American Standard Code for Information Interchange, right, and this has been standardized for computer hardware, okay. There was some other code which EBC DIC, extended binary coded decimal interchange code, which IBM introduced for its device, but this ASCII code is now, you will see it is prevalent, and people are using it, and it is a 7-bit code. So, 128 possible codes are there, right. And if you just look at how things get represented, say one of the character we type, say, is capital A, right. So, capital A, you can see in the example. So, these are the more significant bits x6, x5, x4, and these are the lower significant bits x3, x2, x1 and x0, right. So, 1 0 0 this column, and this row if you see 0 0 0 1 coming from here. This is how capital A is represented. And how small a is represented, you will see that this is small a. So, between these two only one value is changing, this 0 is changing to 1, and rest of the values are remaining same. So, small a is 1 1 0, this instead of 1 0 0, this is 1 1 0, rest of the values are remaining same. That is your small a. Similarly, between capital B and small b, you see that only this place the value is changing, 6th place, right, 7-bit, this is the place it is changing. Now, how 0, if you type 0, how 0 is represented? So, 0 you can see over here, this is 0. So, 0 1 1 and 4 zeros, 0 1 1 and 4 zeros, this is the 1, right. How 1 is represented? This is 1. So, 0 1 1 and 0, 3 zeros and 1. Okay. So, these are the different things out of this say carriage return. So, when you press enter and all. So, then what is the corresponding ASCII code based on which some action is taken? So, carriage return is 0 0 0 1 1 0 1. This list is not exhaustive, right. All 128 options are not given. These are mostly these are the printable characters that you can see. Okay. So, with this we come to the conclusion. A change of more than one digit for 2 consecutive numbers in binary code may give problem in certain applications. If one digit change is slower than the other, for which we discussed gray code, and we have binary to gray and gray to binary conversion using XOR gates. ASCII code is the one where 0011 is added to the binary coded decimal, and ASCII addition and subtraction uses simpler circuit than BCD adder subtractor circuit, and it involves addition or subtraction of 0011, that is 3 in both the cases. And ASCII ASCII code is a 7-bit code by which control codes for peripherals and printable characters can be generated and exchanged. Thank you.